Hello guys, it's the Caribbean Bookworm and welcome to part 3 of our journey to relativity. And in this video particularly, we'll be looking again at the Chronicle delta, which we talked about in part 2. And also we'll be looking a little bit more into the cross product of vectors. So in essence, in the first or in this second part of the journey to relativity, we talked about the dot product as we mentioned some of the basic properties of vectors. When you have a dot product of two vectors, what you get out of it is a scalar. Now, the last time when we talked more and more about vectors, we mentioned things such as the gradient of a scalar function and in essence the different things we can do with using something known as the del operator. And now we'll be looking at cross products and also some of the things we can do with the del operator, but by using the cross product instead of the dot product of it with, say, a vector. So in order to start, let's again look at our chronicle delta. So our chronicle delta was this small letter, Greek letter delta. And we mentioned that this chronicle delta has a symmetric property. And how we show this in the video of part 2 is by writing this in terms of a matrix and show that even if we interchange the rows and columns of I and J, basically you still get the same matrix out of it, meaning that actually the sequence of which we write our I and J doesn't actually really matter. At the end of the day, both of these will give the same sign for the terms of which they are multiplying. So basically, if you have a chronicle delta multiplied by, say, a positive number, then it will still give a positive sign right here, as it will right here if the index order is flipped. So this indicates that the chronicle delta is something that is known as totally symmetric. Now today we will be looking at cases at which the order of the index does matter, whether or not the sign stays the same or the sign changes, and we'll be denoting these so-called anti-symmetric objects very soon. And it's especially important when thinking in terms of the cross product. But before we go on to talking about the cross product, a couple of last things we want to look at about the chronicle delta and the hybrid chronicle delta is, for example, what would happen if for the hybrid chronicle delta we have the same index right here. What would that give, basically? Now, if we remember the definition for the hybrid chronicle delta, it was that in essence you need to have two free indices in such a way that they appear again in the other side of the equation. But in this case, we can see that the i's here, they appear right here, and they repeat themselves in this particular expressions, and a similar manner at which the k's repeat themselves. You can think of it as basically there is a double summation happening right here. And how this would be then expressed is if we were to write this down a bit more formally, so instead of using the index contractions, we wrote it a bit more clearly with summation signs. We would have a summation sign that looks like the following. We have a double summation in which you can have the following expression. From this double summation, in essence, we have 9 terms of these two chronicle deltas. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. And if you recall in when we previously talked about the chronicle delta, what you can think of it is the possible combinations you can have of these two indices or in essence, well, 3 times 3, so that gives you 9. So you know immediately there are 9 elements. But such as we talked about before when looking at, for example, the dot product, we know that some of these are not going to be here because, for example, a particular aspect of that which we define the canonical delta to be is that when the indices are the same, that's where we have a 1 for our canonical delta. And when the indices are not the same, that's when we have a 0. So in essence, a lot of these will fall out, leaving just 3 terms in here. So we will have this be 0. So we will have 1, 2, 3, 4, 5, 6 terms that immediately falls out, and 9 minus 6, that leaves you just with 3 things in there. Because 6 terms in here are all 0, and the only non-zero solutions in these terms are the ones with similar indices, where I and k are similar, then we know that these ones where you have the canonical delta 1, 1, canonical delta 2, 2, and canonical delta 3, 3, we know that only those ones deliver 1 in essence, because we defined our canonical delta to be 1 if I equals j, or if in this case I equals k, so if the two indices are the same, and 0 if else. And in this case, we have then, okay, the canonical delta 1, 1, that will be equal to 1, and because then we have right here that it is this multiplied by this, so the canonical delta upper index of 1, 1 multiplied by the canonical delta lower index of 1, 1. We know that this is 1 times 1, which will just simply be 1 right here. Similar fashion for the canonical delta with the indices of 2, 2, we will have 1 right here. And similarly for the one with with indices of 3, we will have 1 right here. So at the end, our double summation just boils up to 1 plus 1 plus 1, and that is just 3. So we know then that if we have a double summation in which our upper bound, you could see, of our summation is 3, such as what we're looking at when talking about 3D Cartesian coordinate systems, then we know then that the answer to a canonical delta or a hybrid canonical delta in which you have similar indices, that will just simply be 3. A property that will be useful as we go on to see a further example. So with that defined, now we can actually look at the cross product. Now, this requires that you have had a little bit of linear algebra and knowing how you define the cross product in terms of determinants. And you are also comfortable with something known as the Laplace expansion, which basically just boils down a larger determinant to its smaller fragments, you could say. Now let's look at the basic idea of a cross product, and that is that if you have two vectors, say a vector u and a vector v, again similarly as we had before, and an angle between the two, then basically when you take the cross product instead of the dot product, so if you take v cross u, what you get here is another vector instead of a scalar, at least when talking about vectors in 3D Cartesian coordinate system. You get another vector. And the vector is orthogonal to the two vectors given here. So basically you can think of v and u in a particular plane. When we're talking about 3D space, you can think of v and u in a similar plane. So say that they're in the x and y plane. You get a vector that we call v cross u that is pointing in the z axis basically. So it points at a direction that is orthogonal to both v and u, you could say. So now let's remove that. One way in which you can define it, especially in this 3D space, similarly as to how we could define the dot product to be the magnitude of the two vectors multiplied by each other times the cosine of the angle between the two vectors. With cross products, you can think of it as being the magnitude, again, of the vectors multiplied by each other, but this time times the sine of the angle between the two, and also times the unit vector, say E3, that is corresponding to the basis vector pointing in the direction of this newly produced vector. So you can think in terms of the drawing that we just made that it would point in the z direction, and we defined the z direction previously to be something called E3 hat. So we can then say that a way in which you can write the cross product is by having the magnitudes of the two vectors times each other, times the sine of the angle between the two vectors, times its corresponding unit vector. Now let's look at this in terms of the determinant definition, which is a little bit more clearer, in my opinion, at least, and useful for what we want to do. So in the determinant sense of things, in the terms of linear algebra, right now we're going to be using, instead of vector v and u, we're gonna say we have two vectors a and b, because it makes our life a little bit more insightful and easier. We're going to say that, for example, we have a vector a and b that are within the vector space of our tree. So basically, they're within 3D Cartesian space. Well, let's just define it as that. And we want to find the cross products of these two things. So of vector a cross b. The manner in which we will define this, and we will call this corresponding vector that we get vector c, just to make it easier later on to note things, we will say that a cross b, aka c, is equal to the following. It is equal to the following. It is equal basically to the determinant of this 3 by 3 matrix. This 3 by 3 matrix consists out of, in the first row, the base vectors that we have for our given situation. The second row being the three components of our vector A, so AX, AY, AZ, or in index notation, A1, A2, A3. And similarly, row 3 will be the same case as for row 2, but in terms of vector b. So how are we to find the determinants of this? Well, as I mentioned earlier, if you know how to use something known as the Laplace expansion of a determinant, then you can more easily calculate this by saying that, oh, we can pick this first set of information, and that is the element of E1 hat. And if we do that, we just close off the entire row and the entire column corresponding with this element, and we just look at this one particular box right here and try to find the determinant of this little bit right here, which is simply a 2 by 2 determinant that you need to calculate, which is much easier. So what we will get then is that this will be A2 multiplied by B3 minus B2 multiplied by A3, or A3 multiplied by B2. And all of that multiplied by E1 hat at the end. Now, this is the first term you could say of our of what we get with A cross B, and it is also actually the first, at least this little bit of information, it is the magnitude of the first component of this C vector. So in essence, it is the magnitude that you will get if you plug this in with numbers. It is the magnitude that you will get for Cx. Of course, if we were to calculate this further, you need to take into account that if you're looking at such a system, then you have to set your reference frame in terms of what are my pluses and what are my minuses. So if we're looking at this as being plus, we know that this has to be minus and this has to be plus. And well, if you were doing this in terms of another fashion, say you were going from this here to here, then this will be your plus, minus, plus. But because we're writing this in terms of these base factors, we're just looking at this, then we know that this is plus, and now what we're going to get here is minus. So we immediately write our minus sign right here and do a similar process of elimination. For the second term, if we choose this E2 hat, then we will have to take the minus sign right here, as we already denoted, and we will have to find the determinant of A1, A3, B1, and B3. So again, a 2 by 2 determinant. So that will be the following expression right here that you have. And the third expression will simply be, because this is plus, again, we will have plus, and now we choose our E3 hat as the base factor we're going to be multiplying by, and we will take this following 2 by 2 determinant. So now we can see that we have all the three components of our C vector, which is basically the vector that you get when doing the cross product of A and B. So if we are to write each of these components individually, we write them as the following. These are, in essence, by the way, I will remove these base vectors as I just want to represent the magnitude of each of the components of the C vector, so C1, C2, and C3. So in essence, this is what we get for all of the three components. We get that first determinant, which we got multiplied by E1 hat. The second term that we had right here, I will read this right here. And the reason which I wrote it like this is if we multiply this by minus what's inside here by -1, we have plus A3B1 and minus A1B3. So you can just write that as A3B1 minus A1B3. And of course, you have this third term right here. Something that you can notice already that is in a sort of a pattern is that we continually have two indices in one term and the same two indices in the other term. The only thing that changes is when we write it in the front. For example, say if A right here had an index of J and B had an index of I, in this first expression right here, J equals 2 and I equals 3. And in this other expression right here, this flips. So you have basically the indexes flip, and you have A being I and B having the index of J. And that, for some reason, changes the sign of our given expression right here. So we have a property or an object at which if we change the order of these signs, or if we change the order of these indices, it does change its sign from plus to minus. So you can say that this is equal to minus A, I, B, J. And of course, the opposite is true. If I multiply this by -1, you get that. So we can still write this in terms of index notation. Say if we were to write the component of this vector. So if we were to write the x component of this newly created vector C, we would have that Cx is equal to So if we have the x component of this A cross B, of this new vector, then it is, again, a double sum of AJBI. But then again, now we need to introduce a term in here which shows basically what is known as the anti-symmetric property of this particular sum. Because as, for example, when we look at the canonical delta, with the canonical delta, the order in essence didn't matter. If we had the canonical delta ij, it would in essence give the same sign as the canonical delta ji. Like if it's a plus here, it's a plus there. But you can imagine now we have a symbol, a random symbol. Let's call this a curly thingy right here, in which if the order is ij, the same curly thing here would have a negative sign if we switched basically the indices. So this new symbol right here that we're going to be using is the lowercase epsilon, this Greek letter epsilon, ijk. And this is what we call the Levi-Civita anti-symmetric symbol. It's an Italian name, Levi-Civita, I think, of a mathematician. And what this basically implies is the following very weird definition that what you multiply, basically, if you use the symbol to multiply something by it, you would have a value, you can have three values, 1, -1, and 0. So contrary to the canonical delta that you had just 1 and 0, in this case you can have 1, -1, so a change of the sign, and 0. And when do you have a 1 or a -1? Well, you have a 1 for if you have something called an even permutation. Now, how do you find an even permutation? By the way, permutation meaning the specific combination of indices that you use. So if it's, for example, I, J, K, or instead you change the order of these indices and make it, say, J, ik, or whatever combination you want to use. That's what is known as a permutation. How you calculate the permutation for this specific case is by using something known as cyclic permutation, and that sounds like a weird name, but after defining this, when we have -1, I'm going to be showing you how you can exactly know whether or not you have an even or odd permutation. So your answer for this Levi-Civita symbol will be -1 for odd permutations. So we define the so-called Levi-Civita symbol as the lowercase epsilon I, J, K. And these I, J's, and K's in the examples we're talking about can have the numbers, well, I or J or K. These can all have the numbers either 1, 2, or 3. So 1, 2, 3, 1, 2, 3. Specifically, of course, for the vectors that we were dealing with, since you can have AX, AY, and EZ. This implies that the specific combinations that you can get in here are of the following numbers, of the numbers, well, 1, 2, and 3. 1, 2, and 3 are the specific numbers, say, you can have in this symbol. Now, if we were to repeat this again, if this sequence was to repeat itself again, I can write it as 1, 2, 3. If we were to repeat itself again, 1, 2, 3, and you get the idea. It can repeat itself again. Now, if we start reading this from, for example, here, from the 2, and we continually want triplets, because you need to have a triplet of combination, then besides 1, 2, 3, you can also have the combination, in this case, 2, 3, and the start of another one, 1. And add the number 3, and we need to have triplets, then we can have the combination of 3 from the last one, and from the new one we can have 1 and 2. So 3, 1, 2. This, in essence, is what we would call the even permutations, because you're going, in essence, from forwards to backwards, basically. You're going from the front to the back. So you can start with 1, 2, 3, and then you go to 3, 2, 3, 1, and then you go to 3, 1, 2. So for these even permutations, you can have for your Levi-Civita symbol the value of 1, or more specifically of +1, of +1. Now, for the so-called odd permutations, what you would need to look at is the reverse of what we just did. So instead of going from forwards to backwards, you need to go from backwards to forwards, basically. So, for example, the first possible combination that we can have if we go from backwards to forwards is the combination of 3, 2, 1. So 3, 2, 1. These specific combinations for our I, J, and K. Another one is if we move this, well, by 1, and starting at the 2 right here, you can have the combinations of 2, 1, 3. And lastly, another combination that you can have is say move this a little bit more here, keeping in mind that you want triplets. It's the combination of 1, 3, 2. These specific combinations are known as your odd permutations, and they will give you a negative sign, you could say, or a -1 value when you're talking about your Levi-Civita symbol. Also saw that you can have a value of 0 for your Levi-Civita symbol, and that will only be the case if one of these indices are the same. So if I equals J, or if J equals K, or if K equals I, then you will have a value of 0. This is because, in the case of our Levi-Civita symbol, that which we're associating this by, our Levi-Civita symbol, in the case of a cross product, is the following. This is what we are meaning with our Levi-Civita symbol. It is the dot product of one of these base vectors with the cross product of the other two base vectors. And if one of these are the same, say if j equals k, then if we take the cross product of j and k, if you remember the first definition which we used for cross products, and that was the magnitudes of the two times the sine of the angle between the two, if you have the same vectors, then you have a sine of 0 degrees. And a sine of 0 degrees is just 0. So that delivers a 0 value for your cross product right here. And that's how you can already see that if j equals to k, if j equals k or k equals j, then you will have a 0 value for your Levi-Civita symbol. The reason as to why if this index of this vector you have outside, this base vector you have outside right here, the reason why you get 0 from your Levi-Civita symbol if this index is equal to the index of one of the two base vectors in this cross product thing right here is, for example, if you take the cross product of a vector that is on the same plane as this one with another one, you're going to be getting an orthogonal vector, a vector at least that is orthogonal to the one right here. So one that has an angle of 90 degrees with this EI hat right here. And if you think about the definition for the dot product, in which you add the magnitude of two vectors times the cosine of an angle between the two, then if the two vectors are orthogonal to each other, you have an angle of 90 degrees. And the cosine of 90 degrees is 0, hence why you would also get a 0 value if I equals to j or if I equals to k. So this is in essence what you need to keep in mind when we're talking about the Levi-Civita symbol in terms of the cross product right here, and why you have 0 for I equals j, or if any of the indices are the same in this case. So now that we have all that, we can write one of the components for this resulting vector in the cross product as the following. You can write it as Cn, where this n represents n equals 1, 2, or 3 in the case of these three component vectors. This equals to a particular very interesting expression where we have a chronicle delta with the indices of ni times, well, this Levi-Civita symbol of ijk times aj and bk. Now, the reason we have this is going to, we're using index contractions, of course. We're contracting the epsilon ijk with this aj and bk. This gives us, in essence, that sum that we got with, say, a2 b3 and minus a3 b2, indicating that if you flip these indices, you get a minus sign. And this is just going to raise the index that you have in order to represent that this, instead of this lower n right here, you have an upper index of n. Because that is, in essence, how you should denote vectors, as we mentioned before, with contravariant vectors being like the actual vectors that you're talking about. You typically indicate them with upper indices. So in essence, you can think of this as performing two things at once to A, G, and BK. So at first, you're going from, say, your Cn, which your Cn in this case will just be the epsilon ijk times the A, G, and the B, K. By the way, I'm making a small correction right here. In this case, I'm writing this C as C with a lower index of I, indicating this free index we have in the Levi-Civita symbol right here. This is going to tell you is when you have a term in which you have I equals J or I equals K, or one of these indices equals to each other for I equals 1, 2, or 3, and that basically says what you're choosing. Are you choosing Cx, Cy, or Cz? It tells you to get a value of 0 if one of these indices are the same. So the only thing you're going to be left with is this case scenario for j not being equal to k, and that gives you either a positive or a negative value. And one of the main reasons for me not writing this out is because, contrary to, for example, the chronicle delta, where the main way you can find the possible combinations is by doing this times this. So for example, in the case of 3 times 3 gives you 9 basically values that you can get and see which ones are 0. In this case, because you have these 3, you will have to do 3 times 3 times 3. And that gives you a much larger value. That gives you a value of 27 27 different components that you can get for just Cx. And of course, of those 27, most of them are going to fall out. So hence why I'm not writing it down. It's quite tedious, and you can try and do it for yourself if you're curious. But this is in essence what the Levi-Civita symbol does here. And now that you have this Ci component right here, we want to raise this index to show that basically we're talking about a vector or a contravariant vector component or object right here. So in order to do that, we're going to be multiplying, in order to get our n right here, or get our index upstairs, we're going to be multiplying Ci by our canonical delta of ni, where of course you have similar indexes right here, but the n indicates how you're changing it from I to n. But of course, in order for this to be a non-zero value, n must be equal to I. So this, at the end of the day, represents the same thing as this, and that is basically the number of components you have for your vector. One thing you can immediately notice from this is, for example, the number of indices present in the lower index section of this Levi-Civita symbol. It tells you the number of dimensions of your object. So for example, if you have a vector with 3 components, then you have 3 indices. But if you have a vector with, say, 4 components, say with an extra index of L, then you have more components in this Levi-Civita symbol, and you have this times this times this times this way to combine it, which is a little bit more tedious. And for example, if we had an object that just had 2 inputs, I and j, so say a vector of in 2-dimensional Cartesian coordinate system, then you could express this Levi-Civita symbol as a matrix: epsilon 2 1, epsilon 1 2, epsilon 2 2. And if you remember, if anything here is equal to, if any of the indices are equal to each other, you have a value of 0. So for these 2 elements in the diagonal of this matrix, you have in essence 0. Now let's look at epsilon 2 1. If we look at this, you can think of this as an odd permutation, because even though you can go from 1 2, move it, you can get to 1. In essence, you can also do, if you have 1 2, start again here, 1 2. If we're going backwards, what you can get here is that 2 1 is exactly an odd permutation of this particular thing. So I can say that this will give a -1 value for our Levi-Civita symbol, while this epsilon 1 2 gives exactly a forward-backward type of combination right here, and that must be a +1 value for our Levi-Civita symbol. So this is in essence the matrix you can get from our Levi-Civita symbol, given that you're using, say, a 2-dimensional vector, basically. Of course, for higher dimensional vectors, this tends to look a little bit more complicated, and we will not touch those right now. Furthermore, a useful relationship exists between the Levi-Civita symbol and the hybrid canonical delta, or just the canonical delta in general. And that is, if we take the double sum of a Levi-Civita, of the Levi-Civita symbol with varying indices for this one. So for example, for the first sum being for I, j, k, the second sum being for m and l, then we would get on the other side a term that expresses the determinant of varying hybrid canonical deltas. Now, this might look intimidating, and the way in which we get this, well, we don't do that here. We just say that we know that this relation exists for our case. But what is important is if we notice something from what is inside of this determinant sign. We can notice all of these hybrid canonical deltas, they have a particular pattern, and that is that the upper indices of this written Levi-Civita symbols, these indices of m, n, and l, they represent in essence the columns which are within this symbol right here. We can see that this is column 1, n is column 2, and l is column 3. And the lower indices, the ijk's, those represents the rows of what's written inside here. We can see that this is I, J, 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 K, K, K. So these lower indices, in essence, of this first Levi-Civita represents the rows, and these upper indices of this other Levi-Civita represents the columns. And if we write this out, if again we do a Laplace expansion, we can see how we can write this determinant of all of these hybrid canonical deltas in the following form, and you can of course try and calculate this yourself. And you can see how basically there exists a relation between this index contracted Levi-Civita symbol with this expression that we found using lots of hybrid canonical deltas. And from this, we can find very useful relationships between the Levi-Civita symbol and hybrid canonical deltas. For example, say we're interested in if one of these indices, one of the lower indices, are the same as one of the upper indices. So say, for example, if we wanted to know what would be the case, what would this look like if we do a double sum where the index with the third index in both of these Levi-Civita symbols are the same. What would that in essence look like with this long expression using hybrid canonical deltas? Well, let's take a look, shall we? Let's plug in, instead of everywhere where we had else right here, we need to plug in the k. Let's try and see how that looks like. So after having written quite a bit right here, we just basically changed all of the L's that were written in here, changed them for K's. So we have our new expression right here for the double sum of the Levi-Civita symbol, or rather I would say the index contracted epsilon ijk with epsilon upper index and then k. We can see something quite interesting. Earlier we said that when we have, at least in the case of k, an index being able to take the values of 1, 2, and 3, such as in 3D Cartesian coordinate system, if they have the same upper index as the lower index in a hybrid canonical delta, then we would get a value of 3. So very interestingly, we can write instead of writing this hybrid canonical delta, we can substitute these for 3. So for example, this would be equal to 3. This would also be equal to 3. And let's see if we have anything else, anywhere else. No, that is basically suffice. Now that we have plugged this in, let's try to now work these out and write it completely in one, you could say, expression. All right. So we have a very long expression right here filled with products of hybrid canonical deltas. So ideally, we would want to simplify this even further and perhaps make a little bit more sense of this algebraic madness. So let's remove this one so that I don't write too much here on the board, and let's try to simplify things. Now, ignoring everything I've written here, it seems like we have a bit of an algebraic mess right here, right? Like we have a place where we have like 3 hybrid canonical deltas. So how are we going to work with this? Well, interestingly, you can contract this and make it even shorter. You can make this index notation even shorter than it was before. And the manner in which we can do that is, say, for example, we look closely at this particular component. We see right here that we have the hybrid canonical delta, kj, and k, and mi. If, in my mind, ideally, before applying any operations of raising or lowering the index, I were to have all of these as just simple lower index canonical deltas, then I can easily see right here that if I have right here, for example, a sum of canonical delta k lower index kj and canonical delta nk, that the only way this delivers a non-zero solution is by having these two set of indices to be the same. So in essence, k must be equal to j and n must be equal to k. And if that is true, I know that also this whole thing must deliver a non-zero solution if j is equal to k and if k is equal to n. And in this case, of course, k equals k. So I can write this more compactly as, okay, this is canonical delta Jn. So just these two indices, since they must be equal to the same thing. And of course, then I will only have left my canonical delta of mi. Now, if that answer does not satisfy your curiosity, since it's a little bit of a backhand answer, and in a sense, we're treating these hybrid canonical deltas as canonical deltas, we can try to look at this formally by saying that let's look at this problem and write it separately. Let's look at, for example, this hybrid canonical delta, so hybrid canonical delta of kj separately, and we previously defined this as the canonical deltas of ki and the canonical deltas of ij, where I is our dummy index and k and j are our free indices. And our other hybrid canonical delta is nk, and that seems like to be canonical deltas ni in the upper index and canonical deltas of ik in the lower index, where again I is chosen to be our dummy index. The way in which we can contract this, perhaps for a little bit of clarification, I will call my dummy index right here a random letter p, just to make this easier. In this way, we can see, oh, okay, if we're finding the index contraction of these two canonical deltas, the ones with the upper index, so canonical delta ki and canonical delta np, we can see that I must be equal to p. And that indicates, of course, as we did with our lower index canonical delta summation, that k must be equal to n, and n must be equal to p if these are all to deliver non-zero solutions. So p must be equal to I, p must be equal to k must be equal to n, k must be equal to p. You can write this more easily by taking these two canonical deltas with the upper indices and write them in terms of, well, a canonical delta with an upper index notation, well, that basically removes all of the dummy indices that we had. So it removes the i's and the p's, because these are dummy indices for these terms, at least if we're thinking about it in that sense. Typically we can't do that, but let's say we are doing that. So if we write that, then our first canonical delta will be canonical delta upper index of k and n, since those were our free indices in these respective terms. And of course, we want to repeat those on the other side of the equation. Now for our other, what that gives us, if we look at the ones with lower indices, is, well, we have our dummy index of I right here for this particular part, and our dummy index of P here on this part. And we know that in this case, I must be equal to P and J must be equal to K. So we can just drop these. We can drop these dummy indices and just write this this canonical delta in terms of the free indices that we have right here, which are J and K. So, and now, if we look at what we got right here, what we can now, in essence, see is a new notation for our hybrid canonical delta, where instead we now have our k as the dummy index, and our n and j as our new free indices. So in essence, we can write this right here as one hybrid canonical deltas with upper index of n and lower index of j. We pretended that this first index was the upper index of our hybrid canonical deltas, as you can see right here, with n being that, with m being that. And with this, using this analogy, we find that this is Jn. That's hybrid canonical delta Jn contracted with hybrid canonical delta Mi. And we can do this for this term as well with these three hybrid canonical deltas, same as this term, same as this term. And in doing so, we basically hope that some of these terms basically fall out of our expression. because of the fact that we chose for our third index of this Levi-Civita symbol contracted with itself or with another Levi-Civita symbol. We chose the third indexes of both the Levi-Civita symbols to be the same. So knowing that new trick of making these hypercanonical deltas shorter, and also knowing the fact that these hypercanonical deltas with similar lower and upper indices are equal to 3, we can now write this whole thing out, as I decided to write it again in order to try and correct for some of my own mistakes. You can write all of these things again and now see whether or not we can make this more compact. Alright, so we've written the whole thing up here in terms of just canonical deltas with lower indices in order to make perhaps our problem a little bit more clear, basically. So now let's apply the trick in order to make these three products of these three products of canonical deltas a little bit more compact. So let's start with this one. We see here that we have a k and k. This can be contracted and written as just a canonical delta of j and m. Now let's look at this other particular term. Now let's see here. We have mi, kj, mk. You have two k's right here, so you know that these two can be contracted into a canonical delta of j and m. Now let's look again. Let's look at this particular one. We see here that we have a k and a k right here. So these two canonical deltas can be made somewhat shorter into one canonical delta of lower index I and m. And lastly, we can look at this one right here, and we can see that these lower indices contain k and k right here. So we can write this hypercanonical delta, well, the product of these two at least, as a hypercanonical delta lower index I and m here. Now let's see if there are overlapping canonical deltas so that we can make our problem a little bit easier and neater. Well, immediately we can see right here that we have a canonical delta product of mi and jn. And to remember that canonical deltas are symmetric, so no matter the order which you have, that doesn't change the sign. So in essence, what you have here, a canonical delta lower index mi, that is the same as the canonical delta with index im that we have right here. And the canonical delta with lower index jn is in essence the same thing as the canonical delta with index and j that we have right here. So in essence, we have -2 of this particular component right here, because it's this one minus this one. So we can write that as -2 of this right here. And if we look right now, we can remove this last bit right here. If we look right now at the other thing which we contain, we have this these two terms. Same thing applies. We can see right here that this is a hypercanonical delta with not just a canonical delta, sorry, with lower index of ni, and another one with lower index of gm. And again, we look at the symmetric properties. If we sum the n and the I, in essence, we have the same thing. And if we sum the j and the m, in essence, we have the same thing. So we have 2 times the positive of this particular component. So we can write that as +2, while removing this little bit right here, because it's the same thing as this. You can clearly see now that we have a smaller algebraic mess, and we can see that this particular product of canonical deltas kind of overlaps with this one, because again, remember the symmetric properties. The first canonical delta has a lower index of mi, so does this one, and this one has a lower index of nj, and this has one of jn, but due to symmetry, it's in essence the same thing, so we can subtract this 3 times this product right here, minus the 2 times the same product, which gives us just 1 time this product. So you can remove the 3 and remove this, and we're left, in essence, with just this. And now if we do the same thing right here, because if we can see we had our 3 times, well, this particular product, which is what we got originally in here, and now we have the 2 times this canonical delta with lower indices. The ni is the same as here, the nj is the same as the jm because of the symmetry properties. So in this case we have -3 plus 2, which just gives minus the thing that was here. So I will write that more neatly right here. And if I write this now in terms of hybrid chronicle deltas, what I'm left with is this being in essence what we wanted to prove. We wanted to prove and show that if we have the product of the Levi-Civita symbol with itself, with three indices, where one of these indices are the same, that would be the same as this particular bit right here. Now, because basically my phone battery died, I couldn't basically finish the video back at my faculty, so I decided to do it now here at home. By the way, my apologies for the shaky camera for that particular reason, but basically, if we look at what we just found when we found the product of the Levi-Civita symbols, where one of the indices are the same, then what we found was this particular expression, if you recalled. Now, what would happen if two of the indices are the same? So two of the lower indices and one of the Levi-Civita symbols are the same as two of the indices in the upper Levi-Civita symbol. So in this case, n must be equal to j, so that, well, the second upper index is the same as the lower upper index of the first Levi-Civita symbol. Well, what we can find then is simply imagine if in this expression you substitute all of the n's for j's. Then what you see is that, for example, for this hybrid chronicle delta, you have a hybrid chronicle delta with upper index of j and lower index of j. And if you remember correctly, if we have a hybrid chronicle delta in which the upper and lower indices are the same, then by definition we would get 3 basically. So we would say that, all right, we already have 3 times a hybrid chronicle delta of mi minus, well, the n becomes j in this case, so a hybrid chronicle delta of ji and the hybrid chronicle delta of mj. We write that in the form of the lower index, such as what we did with the trick in order to make these hybrid chronicle deltas a bit more compact, basically, in order to do the contraction. Then we will get that we have 3 chronicle delta mi minus chronicle delta ji chronicle delta mj. We can see that both of these contain an index of j, so we can in essence contract these two chronicle deltas and make it more compactly into a chronicle delta with lower index im. So that basically implies that we have, in essence, the same thing right here due to symmetry. So it is, in essence, a problem of 3 minus 1. And that just gives 2 chronicle delta mi. And if I were to write that as it truly is, that would be 2 a hybrid chronicle delta of mi. In essence, this is exactly what you get expressed in the book itself as well. Now, let's look at the final property. If all of the indices are the same, so of both the two Levi-Civita symbols. So for the first one, we have a lower index of ijk, and for the second Levi-Civita symbol, we have upper indices of, again, ijk. What happens here is, well, for the m that we had before, in this case, the only one that wasn't the same as the one of the lower index, what we have right here is basically we plug in m equals I, and you would find a hybrid chronicle delta with similar upper and lower indices, so that tells you that you would have a value of 3 right here. So that means that you would have 2 times 3, and that is just 6. So these 3 properties of the products of Levi-Civita symbols are, in essence, what we wanted to look at when doing our little calculation, and they might come in handy for later again. Now, having looked at these relations between the Levi-Civita symbol and the chronicle delta is important because this in essence tells us something about symmetric and anti-symmetric objects and their relations with each other. And namely, one thing an important theorem that follows from the properties of these things is that a symmetric object contracted with an anti-symmetric object always vanishes. You mostly get 0. And we can prove that, actually. It's a very straightforward straightforward proof. Say we have a random matrix of aij. Aij, this indicates that it is a 2 by 2 matrix. Because it is symmetric, it indicates that if we flip these indices, we still get the same sign at the end, and so in essence they're the same thing. So matrix aij is equal to matrix aji. And now let's say that we have now another matrix, matrix B with lower index this time of ij, and we say that it is a totally anti-symmetric object. That means that if we flip the order of these indices, that basically we're going to change the sign. We're going to get a negative sign. So bij, if we flip that, we will get a negative number. We get negative bji in this case. Now, if we look at this, if we contract the left side of these terms right here, so aij with bij, what we should get in essence should be the right side of these terms, so aji and negative bji. So how we write this is if we contract aij with bij, we should get negative the contraction of aji and bji. What this tells us is if we contract basically this symmetric matrix with totally anti-symmetric object right here, we should get a negative of, well, when the indices are flipped. And there's only one thing that we know, that the positive is equal to the negative, and that is, of course, the number 0. So this tells us that when we contract this, we should get a value of 0, because only then the positive will be equal to the negative, because the negative 0 is, well, it's just 0. This is an interesting property because say now we look at the contraction of a Levi-Civita symbol with a canonical delta. So say we contract epsilon I j k with canonical delta, say of j k. So if we do that, we can see right here that the second and third index right here and here is equal to the two upper indices of this. Basically, if we do this index contraction, what we would get is 0. Because this Levi-Civita symbol right here carries these two indices of jk, and this canonical delta carries the indices of jk as well. And what we know is that if we have these objects which have these same indices, but one of which are basically totally anti-symmetric and the other is totally symmetric, then by this property that we just found, the only viable thing that we should get is 0. If, for example, this use of index contraction didn't make the situation clearer, we can actually express this in terms of the double summation that is actually intended for it. So say we now express it fully, what we would get is a double summation, where one of the summation signs is for the j, with j equals 0, and the other one for I, sorry, not 0, 1, and the upper bound being 3. And now we can write the same thing right here, for example. And what we can see here is, of course, well, the indices add with 1 every time, and it goes on to a bound of 3. So, for example, the first term which we can find is lowercase epsilon I 1 1, canonical delta 1 1. What this would give us is, because we have two indices which are the same here in the Levi-Civita symbol, if you remember, when you have two similar indices in the Levi-Civita symbol, this thing is equal to 0. So because this thing equals to 0, then this whole term falls out. The canonical delta in this case, though, does exist because you have two indices which are the same. So the canonical delta would have a value of 1, but because this is 0, this term falls out. Now let's look at another term. Let's say we have lowercase epsilon I with 1 2, canonical delta 1 2. Let's look at this particular term. In this term, we have a Levi-Civita symbol in which the two indices right here are not the same. So the Levi-Civita symbol might have a value. It might have a value of 1. It might have a value of -1. In this case, the Levi-Civita symbol would only have a value of non-zero when I does not equal to 1 or I does not equal to 2. Because if I equals 1 or I equals 2, then we'd have a problem. This thing becomes 0. If this I equals 3, then basically we'd have an even permutation of 3, 1, 2. You can try and check that out if you want to use cyclical permutations. And this means that the Levi-Civita symbol would give a value of 1. But because the two indices in the canonical delta are not the same, that means the canonical delta will have a 0 value. So this term falls out as well. And this pattern continues. It continues on and on and on. When you have a canonical delta symbol that exists because it has two similar indices, then the Levi-Civita symbol does not exist just for the same reason it has two similar indices. But if the Levi-Civita symbol exists, then the canonical delta does not exist because it has two indices which are not the same. So in essence, from this summation, we can still find that the value we would get by contracting the Levi-Civita with the canonical delta is still 0. Now, generally speaking, a matrix, let's say Aij, this matrix, random matrix, it can be decomposed into a totally symmetric and a totally anti-symmetric part. And it looks as the following, if we note it. It looks like this. Just for notation purposes, we're using these types of brackets to indicate a totally symmetric index object, and here this type of bracket for a totally anti-symmetric index. In this case, we have our totally symmetric component and our totally symmetric matrix, you could say, and our totally anti-symmetric matrix, and basically these are two basically components that can form our or it can form our matrix Aij. Now, we can write for both the totally symmetric component and the totally anti-symmetric component by doing a little bit of algebra right here and saying that A for the totally symmetric component, that is equal to the regular matrix minus the totally anti-symmetric matrix with the original Aij order. Though if we flip this index right here, that would give us a change in sign because this is a totally anti-symmetric object, meaning that this would go from a minus to a plus. Now, if you think about what is happening here, think about, since we're talking about a matrix, think about, say, if we're talking about a matrix A1, 2, or just basically this indicating the rows and this indicating the columns. If we flip the directions right here, that would imply that we are exchanging the basically the columns for rows and rows for columns. That basically implies that when we change the sign right here, we're looking at the transpose of a matrix. So in this case, say for example, if we had a matrix A, then this would be a matrix A, this would be a matrix A, but this would be A transpose. That is another way to think about all that is happening right here. So in this case, then, if say for example, if our matrix was symmetric, then Aj, because it is symmetric, it would be the same thing as Aij. So that would imply that we would have right here 2 times Aij, and in order to even that out, to get our Aij that we want, we would have to divide this factor right here by a half. So that will give us 1 over 2 multiplied by this right here. Give us this, right? This expression right here. Now, if we want to look at the anti-symmetric component, then we can write that as the following. That is equal, if we do a little bit of algebra, send this to this side right here, we will get the regular matrix Aij minus the totally symmetric matrix Aij. And property of the totally symmetric matrix is that if we flip the sign doesn't change of the object. So this remains a minus sign. So that gives minus Aji right here. And By the way, I removed the brackets right here, and the brackets right here. In essence, nothing else changes. It's just that if this is a totally symmetric object, then the order doesn't change the sign. So you have 2 times this right here, and this still holds. But now for this one, if you change the sign right here, we have AJI, then that does imply a change in sign that makes this a negative object. And a negative, well, if multiplied by -1, that just gives you positive. So if this is a totally anti-symmetric object, then we would still have AIJ plus, well, the factor that we have right here. So for that reason, we can, if we wanted AIJ at the end, because of the fact that we will still get to AIJ in here, we will want to divide it by 2. So we can express then this term as half times AIJ minus AJI. One last thing that we will look at is the so-called curl of a vector field. And what this is think of it in terms of a water stream streaming through the ocean, for example. Now, if we were thinking in terms of 3D Cartesian coordinate system, say if we had a place at which the water is somewhat rotated, like it spiraled downwards and downwards. You might think that in this case we're dealing with the case of another divergence, or in this case convergence. But in this case, since the things are spiraling downwards, then we are dealing with water that is spinning in a vortex. And if we were to place something like a topper that spins, it will spin, for example, in a counterclockwise direction or in a clockwise direction. For example, with respect to x3 or with respect to x2, if, for example, somehow we measure something that measured the rotation in this direction, or in with respect to x1 that comes out of the paper, if we had something that measured the rotation in that direction. And conceptually, this is what we define as the curl. The curl would be looking in essence at the concentration of vectors that are rotating about a particular point, and we can look at this. If there is no curl, then there is no water streaming around a particular point. For example, the water is just streaming in this direction and in this direction, in this direction. It is streaming randomly and not along a particular fixed point. Now, mathematically, how we look and find the curl of a given vector, for example, is by taking the cross product of the del operator with a given vector, say vector v. This, in turn, because we're taking the cross product, it gives another vector, vector u. And the way in which we can think of it is, for example, think in terms of physics. If you are applying a torque on a particular object, then what you're getting in that sense is an angular momentum that is pointing perpendicular to the surface at which you're applying the torque. If you had a little bit of physics, you can imagine what I'm talking about, but more simply said, say, for example, you had a bicycle wheel, and you're applying a torque, say a force, onto this direction of the wheel. So you're trying to rotate the wheel to get it to spin. You're applying this force known as a torque. Then the angular velocity which it will get is actually a vector that is perpendicular to the torque right here, to the plane of the torque. And you can denote that as the angular momentum, my apologies. And it is in essence 90 degrees, or in essence orthogonal from the torque that you get, basically. Well, a similar philosophy applies well in when looking at the curl. The curl in this is produces in essence of a new vector u, which is what you are in essence, say, for example, measuring by placing a topper in this particular direction of a streaming water. And the way in which we can mathematically calculate this, of course, is by finding the determinant with the del operator having its x, y, z components being the partial derivatives with respect to x, y, and z. We of course wrote them in terms of index notation. The components of the vector v in 3D Cartesian coordinate systems being v1, v2, v3. And if we do a Laplace expansion, then we can easily calculate for this 3 by 3 matrix by seeing that this first component is, say, if we take E1, isolate these bits and find the determinant of this area right here, that would be this multiplied by this minus this multiplied by this. It will give us this value. If we look at the second term, if we look at E2, this would have to be a minus sign right here. So it would be minus, this times this, which would be the partial derivative of v3 with respect to x1, minus the partial derivative of v1 with respect to x3. Now, if we change the signs, because we had a minus sign in the front, basically what we will get is this, instead of being the negative partial derivative of v1 with respect to x3, it will be a positive value, and the positive value that we had will be a negative value. That's what you see right here, that this, instead of a negative value, will be a positive value, and this will be a negative value instead of a positive value. Now, the third bit is a bit more straightforward, and that is if we take this, then we take the determinant of this particular bit, and that is, well, partial derivative of v2 with respect to x1 minus partial derivative of v1 with respect to x2. Multiplied, of course, by the base unit vector. These, in essence, are the three components of our vector that was produced by taking the curl, you could say, of vector v. And very compactly, we can write this using the Levi-Civita symbol and the shorthand notation for partial derivatives that we discussed in part 2 by saying that if we have a Levi-Civita symbol with its first two indices raised and one lower index, we would in essence have expressed the same thing right here, but in a more compact form. If we unpack this, we can see this to be true. For example, we can see right here that there are no free indices. All of these are dummy indices, and you have, for example, a k written in the lower index right here and a k written in the upper index right here. So that already gives you a summation. We have I written in the upper index and I written in the lower index right here. Again, another summation. We have a j written in the upper index right here of the Levi-Civita symbol, and another j written right here in the lowercase del. So that indicates another summation. So in essence, what you have right here is a triple summation instead of a double summation. You have a triple summation, and that in essence, if you plug these in, gives you the same result right here. And if you want to, for example, get into the nitty-gritty of how you can raise these indices of the Levi-Civita symbols, you can try that for yourself as a fun exercise right here. You can see that, for example, you have your typical Levi-Civita symbol of smaller case epsilon I j k, and if I multiply it, for example, by this chronicle delta I n, it raises the I index above, and it typically makes that a letter n, which I wrote right here. So you have epsilon upper index n jk, and now you multiply what you got right here by this other chronicle delta jp, and that basically raises your index of j and converts it into p. So now you have this epsilon and p k. And now all we need to do is change these two indices to their original I and j, and that we can do by multiplying this this Levi-Civita symbol twice by a hybrid chronicle delta, which converts the n into I right here and the p into j right here. That is in essence how you can get to raise the indices right here for these Levi-Civita symbols, so that you can still imply summation in essence by raising your dummy indices. So I hope you guys enjoy part 3 of this journey to relativity video, and of course there's more to come. This was quite a challenging one as it took quite a bit to get used to the Levi-Civita symbols, and especially the product of two Levi-Civita symbols and these different index manipulations and such. It's still quite new, it's still quite fresh, so I don't blame you if it's quite confusing for you as well. For me, what I did is I used a book, which I'd highly suggest you look into and see if you can find it perhaps online. But if you can't find it online, I'd suggest you try to look for YouTube videos as to the bit where you got a bit confused on. I did that myself for some bits, and even though you do find some videos, do keep in mind that it is a little bit difficult to come across some videos on some of these topics because they are already getting within a little bit more of a niche territory. So you might have to be a little bit more patient if you're looking for online videos for some of these topics. But I hope I have explained some of these concepts in the clearest fashion possible. And in the following video, in part 4, I'm going to try to and hope to make it a little bit shorter by dealing with less content than I did in part 1 to part 3 right now. In part 4, I'll simply be looking at vectors in curvilinear coordinates, and that will be a video on its own, not because the paragraph is very long, but because I want to basically make a shorter video, a more digestible video for you guys. In part 5, basically, we'll be looking a little bit more closer into vectors and then finally delve into the realm of tensors. So I hope you look forward to that, and I hope to see you guys very, very soon. Bye.